Most of you know me. I'm John Fasella. I'm a past president of RCA, and David Bart is president. And We have been doing this interview series for several years now, as I said earlier. And we have very lucky to have Steve Floyd. Steve has given two presentations at our technical symposiums, one this year in Denver and one last year in Atlanta. And his presentations are very interesting. So, Steve, why don't you start off by giving a quick summary of your own background?
Okay, sure. Well, I got interested in radio science and radio in general as a very young child, around 8 or 9 years old, actually, as a shortwave listener. I got my amateur radio license and became very active in local radio clubs. I ended up meeting a lot of electrical engineering professionals and ended up going to Virginia Tech and completing a Bachelor of Science in Electrical Engineering degree in 1980 with emphasis on RF and microwave engineering and communications. And then I went to work for E-Systems, defense contractor, which I guess we'll talk a little bit about later, some of those projects. But then after about 7 years, I then went part-time to the Johns Hopkins University. I live just west of Washington, D.C. in Northern Virginia. So I was commuting up to the Johns Hopkins University Applied Physics Lab for classes for a master's in EE, and also sometimes to the Homewood campus. I did it part-time because I couldn't afford to pay all that tuition myself. The company paid for it, thankfully. But after 4 years of very difficult work, I ended up double majoring in radar systems engineering and RF and microwave engineering and was an honors graduate, thankfully, from Johns Hopkins. And then in the 90s, after many other projects, got onto the HAARP program that we'll be discussing. And after a long career, I'm now just a part-time consultant and mostly retired.
No, that's great. Great summary, Steve. Thank you. So, speaking of HARP, that was one of the last things you said. I believe there's some misunderstandings about HARP, whether it's still operational or not. You want to elaborate on that, please?
Sure, yes, very good. HAARP, we completed the HAARP project, as you'll hear more about, in 3 phases. And the last phase, the full completion, was in 2007. Now, in 2013, there was a lot of politics of money going on in our federal government. And the Air Force Research Lab, who was managing the program at that time, lost all their funding for research and development. So the HAARP program was shut down for 9 months, and only 9 months, completely. And then the staff was brought back after 9 months, and I was brought back as part-time. The site came up and ran beautifully, amazingly, after that period of time. And in 2015, the University of Alaska, out of Fairbanks, the Geophysical Institute, took over the project in full, and they are operating it to this day. And that they started in 2015. I'm a part-time chief engineer still to the site, working with the University of Alaska and my good friends that are the maintenance team up at the site. And HAARP is very active. So it was only a 9-month pause.
Great, great. Okay, well, hopefully that clears that up. HARP is still on the air.
Oh, very
So,
much so.
so Steve, you said you worked for a number of defense contractors and a number of interesting projects. Why don't you tell us about a couple of those that you can, in fact, talk about?
Okay, well, there are many, but I graduated from Virginia Tech with a bachelor's in EE in the summer of 1980. And I went to work for E-Systems, which was, Fortune 500 firm, excellent company to work for, hardware focused. And I worked on many, many projects there. Two of note. One, I worked on a project called Mystic Star. And Mystic Star at that time, it was a long running, and we did a big upgrade, big redesign. It's a worldwide HF and satellite based communications system that was in place to provide worldwide comms to what's called the Special Air Mission Fleet of our federal government. And that's all the cabinet people and on up, to include Secretary of Defense and even Air Force One when it's in the air. So that was a very demanding, very interesting program. And the net control station was at Andrews Air Force Base right here in Washington. So that was very, very interesting. Another interesting project of note was one called the Tactical Remote Sensor System. And again, we're now in the very early 90s. And VHF packet radio, not the amateur formats, but professional VHF anti-jam packet radio was becoming very big. So I was one of the lead designers where we designed a series of handheld radios with LCD displays, very rugged, militarized, and designed against established protocols to not only communicate to other handhelds on the battlefield in packet radio technology for text messaging, but also there was a line of sensor devices that are oftentimes airdropped or remotely placed that can pick up seismic activity. They had cameras, all kinds of personnel detection technologies, and they would lay in wait with very low battery consumption, then blast out packets if they got activity in the area. And then I also was leading the design of a very successful store and forward packet repeater. So these special forces could go to mountaintops or, on the top of a building and conceal these battery-operated store and forward repeaters to get better range and effectively forming a mesh network. This was all in the early 90s, all militarized, very, very successful project. That was a lot of fun. And lastly, I worked on a lot of L-band radar projects. I can't talk too much about the exact applications there. They were very necessary in the Cold War, but I got an enormous radar experience operating on land-based high-power L-band radars during that time.
And I was assuming that that's what you had your radar training by then, right?
Yes, I finished my master's EE from Johns Hopkins in 1991. So yes, that was that radar work. Actually, it preceded that graduation at one point, but certainly was very active afterwards.
So speaking of radar, tell us a little bit about Merle. Is it Slonick?
Skolnick.
Skolnick. Okay, I was right the first time when I wrote it. He was at Johns Hopkins, and I understand he was the editor of the third edition of the Radar Handbook, and you had a chance to work shoulder to shoulder with him. Could you tell us a little bit about that?
Sure. That was an unexpected surprise with my master's degree education at Johns Hopkins. Merle Skolnick at that point had moved over to the Johns Hopkins Applied Physics Lab. And not only was he active in the laboratory there, which is an incredible place. I mean, these are people who are so bright and they're very hardware focused. And so he was doing a lot of radar work, but he also taught master's degree classes in radar engineering. So I decided to double major, as I mentioned, there at Johns Hopkins. So I took 3 classes that were taught every week by Merle Skolnick. And I certainly knew who he was, and I was in awe at getting to know him so intimately in the classroom. And we did have labs. He assigned homework every week, and we had labs where we had to go off and build things. And he would grade our work, which was a little intimidating. But what a nice but extraordinarily brilliant gentleman Dr. Skolnick was. And he actually wrote many books. He wrote all of the introductory books at that time in radar. And he wrote, some of the more advanced books. So I took Principles of Radar 1 that go through all the very basics. And boy, he was tough. I mean, he really demanded that you knew everything. And we had to recite the radar equation on the spot at any time. And he said, you will know this radar equation, which is the fundamental of a radar system performance. You will know this for the rest of your life, as well as you know your middle name. And he's right. So I took Principles of Radar 1, and I survived and did very well. A lot of folks washed out. And then I took Principles of Radar 2, again, a lot of practical lab work, and brought us up to the current day. And then he said, when I have a really, really sharp group of students, I go into, he had this big, I can't remember the exact title, but it was his latest book and the class was Advanced Topics in Radar, which got us right to the state of the art. And he said, when I have a really sharp class, and if I get enough people to enroll, I will teach that. And he did. And I took that class and did very well. But again, difficult, but a nice gentleman and so brilliant. What an experience.
Engineering is not for the faint of heart.
No, it's not.
So perhaps uniquely for many people, you also knew another notable person who was, and I don't remember his name, you did tell me at one point, the Russian engineer who was in charge of the Soviet transmitter program during the Cold War and actually developed the Russian Woodpecker transmitters. Can you tell us a little bit about him and what was his name again?
Yes, that's Dr. London. His Russian name is Dr. Seaman London. And that was such a nice friendship. He's passed away now, by the way. But what an interesting gentleman and an interesting story. When I joined the HAARP program, which we'll be talking a lot about more here later, but I joined that program in 1995. And in 1997, the program office was in Washington, D.C. We hired a couple of Russian PhDs because things were very open with Russia back then. So we had two Russian PhDs that were hired, and they both emigrated through Israel and came direct to the United States to work with us. And one of those two was Dr. London. Now, Dr. London, he was probably in his maybe pushing 70 at that time. But he arrived here, and quite sadly, he arrived with nothing but the shirt on his back for him, his wife, his daughter, and his two grandkids. All of their luggage exiting Russia, which was brand new luggage to put their keepsakes in, was stolen. And he arrived at Dulles Airport literally with nothing but the shirt on their backs. But he was a very kind man, very hard working. So he was brought in to help us design HAARP. He did become a citizen of the United States, and he loved living here, no question about it. So I worked hand in hand with him, and I quickly discovered that he was the head of one of the major transmitter design bureaus in the Soviet Union days for most of his life. And he was the lead designer of the Russian Woodpecker radar transmitter site, which was, it's not the pictures that you see so often that are right near the Chernobyl power plant. The transmitter site, as is often the case for HF over the horizon backscatter radars, is 40 to 60 miles away to get ground wave isolation. So the transmitter site was in Lubick, I believe it's called, up in the northern edge of Ukraine. And so he explained everything about that site to me. They were using 28 individual water-cooled power grid tube transmitters. Each transmitter was 100 kilowatts, and there were 28 100 kilowatt transmitters into a phased array of dipoles. And he was very, very proud of that site. He said the transmitter site worked great, very, very proud of it. And he said all 28 transmitters, which were quite large, as you can imagine, were in a long hallway. And he said he would get in a golf cart and drive up and down the hall to visit the control panel. And when you walked inside of each transmitter, it was a 2-story level to support all of the cooling and all of the RF transmission and stuff, back in the technology of that day. So I learned all about it. And he did share with me one interesting fact. He said that when they were getting these transmitters accepted by the military, he kept getting a question, what are all these parts? And he said, those are my switched harmonic filters. And they said, are those absolutely necessary for this to work? And he said, well, no, but we need to suppress our harmonics. And they said, don't care, take them out. So he said, many times when you were hearing us, it could have been a harmonic because of the gain of the array. So if you assume about a 10 dB average gain of the array, which would vary by where they're transmitting, you're looking at, a 20 to 30 megawatt ERP signal that they were transmitting. But he laughed and he said, "Oh, I know, it's too much power." But what a pleasure to get to know him. He was such a gentleman, a very kind-hearted man, and he passed away about 4 or 5 years ago. He lived in Rockville, Maryland, as a citizen.
Too bad. So something you said the transmitters were, did you say 60 miles away?
I think they were, I've looked it up on the map. I think they were 45 miles away, airline miles from the much larger receive array that we see pictures of so often on the internet.
So they were had transmission lines that were 40 miles long, bring the RF to the array? Do I
Oh, no.
misunderstanding?
No, so the way these over and this is kind of a classic configuration for these high power over the horizon backscatter radars is the transmitter site will be separated because the ground wave
From the
isolation is
receiver.
quite large from the
Okay.
receiver. So the transmitter site has all the transmitters there at the transmitter site, and they typically have a much smaller transmit antenna with crudely steerable beams and lower gain because of all the high power matching units and high power transmission lines. And all they have to do is time synchronize the two sites. And then the receiver site is kind of standalone, but has the proper synchronization. It has a much larger antenna for much more narrow beam widths to knock down atmospheric noise and to pick up receiver gain with a much finer more narrow beam with much larger antennas for the receive site because the transmission lines are so small and the matching units are so small. And in fact, the receiver site has a low band array and a high band array. If you look at the pictures, there's a small and a large for the receiver. The transmit site just had one array that was broadband.
Hmm.
So
it was the receive and transmit sites that were separated by about 40 miles.
Right. And they just had the proper synchronization between the two.
Okay, that makes perfect sense. So, switching gears a little bit, I understand that you had some problems with HAARP with some of the matching networks, the RF matching networks, and this Russian engineer helped you with that. Could you explain the problems and how he solved them?
Sure. So as we were working out some of the issues that we were finding in the HAARP site, and just as a quick backdrop, we built the HAARP facility in 3 phases, and I was the chief RF design engineer at the site over top of everything hardware except for the power plant, basically. That's an enormous site, an enormous challenge. But for the HF transmit array, which we call the Ionospheric Research Instrument, we built it out in 3 phases. We had 18 towers. Then we went up to, 36 towers, I think it was. And no, I'm sorry, 48 towers. We had 18 towers, 48, and then 180. So when we were at the 18 tower level and we got our transmitters designed and working, and we got our matching units on the towers and working, we were transmitting and starting to do science, but we discovered a problem. We had our antenna matching units feeding the dipoles that are suspended by the towers. The matching units were failing at an extraordinarily high rate. And we were trying to figure out what was going on. We thought it was manufacturing problems, but it turned out, and Dr. London was the one who recognized this, diagnosed it, and taught us about it. I had never heard of this. But we had, through mutual coupled RF energy by the close proximity of the dipoles in the array,
Hmm.
Had RF energy that's in what's called the even mode, which means the voltage polarity is the same on both halves of the dipole from mutual coupled power, from neighboring dipoles, many dipoles away even. We had this mutual coupling effect that we could see in the odd mode, which is opposite polarities on either side, either half of the dipole, which is what can radiate. But we didn't realize we had this even mode, identical polarity on both sides of the dipole, energy on these dipoles from neighboring antennas. And that was causing voltage maximas and current maximas within our matching units far beyond what they were designed to handle. I had never heard of even mode power. And so he identified this problem for us. And then when we measured it and verified it, we had to completely redesign new antenna matching units that basically they're fixed tuned, they're round cylinder cans. And he was the lead designer, and I was his right hand man to design it and figure out how to build it and to understand it and work with him. But the key point here is he identified the even mode coupling problem that was creating hotspots of even mode power that would move around in the array, multiple hotspots dependent upon frequency and phase. And we had to do something with this power to manage it. It can't radiate. It was trying to return through the matching units, this even mode power, and find a way back to the source. And so it was giving us tower currents as well. So he came up with a design that I worked with him on where we built a 4-port coaxial TEM mode hybrid transformer wound on air. We were never allowed to use ferrite because we didn't want it to saturate and create harmonics. So it was a custom built hybrid transformer that had a reject port for even mode power if it's there. This 4-port hybrid transformer also had the Ballon function, it had broadband impedance matching and so on. So it really met all of our needs. We had lumped LNC and some vacuum relays and so on. But it gave us this port that if the even mode power was there, it would be sent out a reject port, and I had a convection cooled 50 ohm load that I mounted and paired with each antenna matching unit. So if that even mode power happens to be there, which it would be hot spots all over the array that would come and go and move depending upon frequency and phase. If it's there, it gets wasted off as heat. And that stabilized the array, and the antenna matching units were beautifully built. And he robustly solved that problem for us. And I learned a lot. And that was his contribution to the program.
So that even mode is a dynamic animal, right? Because of frequency and phase changing, it might bounce around to different matching units and manifest itself in different matching units. Is that correct?
Right. Yeah. It's not so much that it's bouncing around, but if you imagine a 180 tower array, and the towers for the low band, there are two different sets across dipoles that are stacked. Our own Dr. Jim Brakall innovated this because we had to come up with one array to cover the whole operating band rather than two arrays that we originally proposed, which would have been horribly expensive. So we had to come up with a common, one array that would cover the whole operating band. So Dr. Brakall came up with a unique approach where we could float dipoles not in use, and we had high bands or quarter wave off the ground screen low bands, quarter wave off our suspended ground screen higher, and whatever band you're not using, you just open circuit through vacuum relays and they would just vanish, which was brilliant. So we used that technique Dr. Brakall brought to us. But what this meant was we had to space all the towers close enough so when we're in the high band, which is up to 10 megahertz, we don't get grating lobes. So that meant in the low band, we were not optimally spaced. The dipoles were very close in the low band because the towers were close. So we traded off gain in the low band to get one array, but it put the dipole edges are only 12 feet apart to the next tower. And so we're so closely spaced on the low band. This is where we got the dominant mutual coupling. And so we would have multiple hot spots, that would be built in the array of this even mode mutual coupled power that we had to waste off as heat because it can't physically radiate like the odd mode can. And so if the beam is statically pointed, and depend upon frequency and phase, we would get vector sums of even mode coupled power at different points all through the array. And then if we're dynamically scanning the beam, these points would move around. But if that power was there, we just wasted it off as heat. And the odd mode mutual coupling would just make our VSWR go up and down. We called it an active impedance, and our transmitter could handle that.
Very, very interesting. And not a common problem that most people would encounter, right?
Right. And boy, did I learn a lot, but he had the experience and the knowledge, and our neck models did not show this even mode coupling to us. It's not really meant for that.
Mm. So you've had a quite a successful career. You've worked for a number of different employers. And I think when we chatted earlier, Steve, you had suggested some career advice that you might have for some of the engineers that are listening. I think in general, engineers are not that great at their careers. They're more focused on the technical problem. And then one day, after 4 years, they say, gee, I haven't been promoted. I'm doing the same old, same old. So what advice would you give to engineers and technicians career-wise?
Okay, well, I'm going to tell you the brief advice and then tell you just a quick experience here that directly applies to HAARP. The first thing is, as an engineer, we're passionate about what we do. We like to learn, we like to create, we like to solve problems, and we like the satisfaction of a job well done. So the first thing is to identify your passion. What is it in the engineering industry and the radio industry in this case that you're really passionate about doing? And then network and discover opportunities yourself. The best jobs are often never advertised. And then the second piece of advice is don't be shy. Go out and meet and greet and introduce yourself to organizations and people that are doing the work that you're passionate about, and tell them about yourself and be curious. And you'll oftentimes get a job offer to follow your passion where you're likely to be most successful, where no job was ever advertised. And I wanted to share briefly how that worked for me with HAARP. So I had completed this master's degree at Johns Hopkins, which was really the best educational experience I've ever had, but it was difficult and it was challenging. And we had homework, we had labs, the people teaching were brilliant, and it was an exercise in endurance and strength like I've never had to put forth before, but it was the education of a lifetime. So after completing that, I went to my personnel department because it was not being recognized at the company that just paid for all of this. And I said, I'd like to do something more. I'd like to take advantage of this and this new education, and I'd like to give you a return on your investment. And every time I went to the personnel department, they just kept saying, oh, just be quiet and go back to your office. They had no interest in helping me grow. And I thought, what did I do all this work for? It hasn't brought me any advancement or any new challenges. So I was looking at different job opportunities, and one day, a company brochure came across my desk because I was a project engineer at the time. And I saw there's a whole list of projects that are going on. And on one of the back pages at the very back, I saw this one like 3-sentence summary about this HAARP program that had been sucked in as a sidecar on another company acquisition. And it just had Dr. Rami Shaney, Washington, D.C., HAARP, and it had a little postage stamp picture of a prototype HAARP tower. And of course, I saw that and I went, whoa, that's what I'm interested in, radio science and high power RF. So I figured out how to contact him. I called him on the phone and I said, I'm an RF guy. I have some experience. I'd like to get involved with this. And I was told, no, don't need anybody. Don't need any RF guys at all. And I thought, oh, it's right here in Washington, D.C. So I said, well, can I come in and meet you guys? I just want to know about this. I'd just like to meet you folks. And he's like, well, okay, sure. You can come on in and just meet us if you want, if you insist. So I insisted. So I got in my car, drove down to Washington, D.C. with an appointment that I made just to meet them. And I said, who is your RF guy? And they kind of said, well, we really don't have one. And I said, what? How can you not have one? This is an RF project. So I did a meet and greet and met everybody, and they were all very nice and very bright, but not really very practical. So I thought, well, that was interesting, but that was a bust. Well, 3 months later, I get a phone call. How soon can you start? And I thought, whoa. So I gave a 2-week notice and did a company transfer over to the HAARP project. And then I quickly discovered that the HAARP project had effectively collapsed because they tried to write specifications and subcontract all the hardware out. And there was so much innovation that was needed. There were so many problems. The spec was so difficult that the subcontractors, they had a spec. They wanted to get in and get out, get their profit. They were not in a position to innovate. They didn't understand. They didn't have buy-in. So the next thing I knew, in 6 months, I was in charge of all the hardware and the RF engineering from DC to light, the networking and everything. And I thought, what have I gotten myself into here? This is bigger than big. But we hired up, we brought it all in-house, redesigned the whole thing over a period of a number of years, and ended up not only meeting all the specifications, but beating the specifications handily and innovating well beyond them. So the moral of the story is discover your passion, network, be curious, and be assertive, and make your opportunities happen.
Wow, that's a powerful story. I'm going to add something of my own to that, but in the meantime, it's almost time for questions from the audience. So if some of you would go ahead and start putting in either the chat or the Q&A questions for Steve, I will forward them to him because, as I said earlier, Barney is not able to moderate. I also want to give a brief infomercial for RCA. Most of you are members, some of you may not be, but of course we're the oldest wireless professional society in the world. And we just finished our annual meeting in Denver, which was really good. The Tech Symposium videos, I'm not sure if they're up, I haven't checked, but if they're not, they will be shortly. We had some really good presentations. I also want to wish everybody happy holidays. It's that time of the year when we all start thinking about family and having fun together. And also, our next interview will be in March of next year. As I said earlier, these are quarterly now. And if you have any ideas or suggestions for topics or what have you, please forward them to Amy at Radio Club of America. And that will be useful in finding new topics for next year. So I just want to second what Steve said. I worked for Motorola for 20 years, and except for the very first job I got, I had a lot of jobs because I was ambitious and wanted to move around a bit. And every one of those jobs thereafter was of my own making. HR or my own boss never really had a handle on that at all. And so Steve is absolutely right. You have to take care of yourself. Nobody cares about your career more than you do. And you got to overcome whatever shyness you may have and just make it happen. Okay, so so far I've only got one question, so please send some questions to us. Let's see. So one of the questions I had was, Steve, would you talk a little bit about your contributions to Flex Radio and also about being an audiophile?
Oh, sure. Well, first I'll talk about being an audiophile. Back when I was growing up as a young child, my best friend, who was also a radio amateur, his father was an audiophile. And I played the trumpet as a child. I was in the school jazz band and in the concert band, and I loved music. And so my best friend's father was was always playing music. He was into high-end audio, and he put up an FM only antenna on the roof of their house to get the local classical music public radio station, and I helped him do that. And so I ended up working on audiophile projects um, with him, and I thought, wow, this is incredible. I've never heard music this clear. I get to explore all this beautiful music. It helps me relax. And so I was interested in both the technology, and the magic of making reliable, realistic, imaging, three-dimensional imaging of sound and so on. So as I went through my college years, I became the chief engineer and a disc jockey at our college radio station at Virginia Tech, WUVT FM, a free radiated FM station, and applied my interest in technology, audio processing, and music there. And that was a great learning experience. And as I've gotten older, I've been able to enjoy building quality audio systems in a well-grounded way. I'm not throwing money at jewelry here like many do, but I can't tell you how much fun it is to discover and listen to high quality music with high quality components and to learn about the science and the engineering and go to the audio shows. I do enjoy classical. I like jazz. I like rock. I like electronic music, folk, bluegrass. I love all these genres, not too much into rap, but I'm too old for that. But it's a great, great hobby. Now, Flex Radio, that's one of the preeminent software-defined radio companies in the amateur radio space. And I got onto them many years ago with one of their early radios, and I've been a consultant and a alpha tester for their hardware for many years. And it's a great, bright bunch of folks. I learn a lot, and I have a lot of fun testing out new hardware and helping them to develop their products. And they pretty much comp me with new equipment. So what's not to like?
Yeah, that's great. Well, what about Flex Radio? They make amateur radio, SDR, software defined radios. Did you have some? Did you give them some assistance?
Yes, my help there is not so much in the software, but it's more in the hardware space where I'm the strongest. It's interesting in the radio industry now. It's absolutely correct to get into the software domain as quickly as you can. And their radios are direct sampling SDRs, as are many, certainly in the government and military space, they certainly are. And that's a very good technology and has huge advantages. But you still have to go to analog in and out, and you have power amplification and all kinds of analog things going on around the digital core. And that's where I've been able to really help them out with power amplifiers, filtering, front ends, all kinds of the analog and hardware development around the software. And that's been really valuable for Flex because oftentimes people that are so good with digital and software are just not aware of the art of analog hardware.
How true that is. So since we're talking about SDR and Flex, that's become a bit of a revolution. What do you predict the impact for AI on radio firmware and software on digital radios, including amateur radios? How do you think artificial intelligence is going to affect all of that?
Oh, there's work going on in that area at Virginia Tech is heavily involved in that area. And I believe the term is called cognitive radio.
Mm-hmm.
And I wouldn't say I'm an expert in that field by any means, but the bottom line is that when you have SDR radios where both the transmitter and the receiver can generate any waveform you want, what an advantage. So a cognitive radio, which they are building these days, you can take a radio in whatever application market it's going to be, military or civilian or whatever, you can take that radio and you can plug it into an antenna, and it can look at the spectrum around it, and it can say, oh, I see I have this standard going, and I have this standard, and I have these transmitters here, and I got this open spectrum here. And it gets not only a full picture of available and occupied spectrum, but it also can immediately assess, well, with some observation time, it can assess what modulation standards and what users are there. And then it can configure itself automatically to operate within those standards to go on to whatever networks are there. And the user doesn't even need to know about much, or if anything, about this. And it's an extraordinarily powerful technology. And then, of course, when they look at the interference environment, whether it be noise or jammers, the AI dynamic concept can also reconfigure the radio to be survivable with those negative aspects of the spectrum environment. So it can immediately figure out what it needs to be. It can be that, and then it can figure out what its performance needs to be in order to survive in its environment. It's phenomenal. So in the amateur space, this is coming.
Yes, I completely agree with you. So we had a couple of questions from university students. So one of them was, what was the most useful college course that you took or that you might recommend? Now, of course, within your sphere, that's going to be largely RF centric, I assume, but there might have also been some other courses that were not RF centric. So you might want to answer that in two ways, RF centric and not RF centric.
Right. And that's a great way to frame the question. Here's how I would answer that question. The first thing is, obviously the first couple years of an undergraduate program are all of the engineering basics, and you certainly, want to master those. But as you go into the engineering courses, you're allowed to specialize a little bit. So try and discover your passion. But in the RF and radio science field, I would concentrate on courses of RF circuit design, where you're learning how to use a network analyzer and a spectrum analyzer, and you're learning all the practical aspects of RF circuits and RF circuit design, and how to use the common pieces of test equipment to make measurements, because these are so important. I would recommend taking an antennas class. I would take a class on power and power supplies. That's very important, always a part of the RF design. And I would also take a control systems theory class, because so many RF circuits, like a phase-locked loop for a frequency synthesizer, for example, you're always faced with control loops. So you want to take a control systems class. Now, in addition to those things, I would definitely recommend that you take an engineering economics class, because one of the biggest shortfalls that I see in the engineering field is engineers that don't have a concept of cost and investment management. And there's two sides to this. There's the business side and the personal side. Now, the business side, in order to be successful, you have to be able to maintain a budget and a schedule, and these are practical financial skills. And an engineering economics class is critical. You must have these engineering, economic, financial management skills to help adjust your schedule and to pace your designs and to satisfy management. Now, on the private, personal side, you must learn how to save and invest for your retirement. I know your parents have been harping about this. But you must realize that on day one, you need to start saving for your retirement, learn about tax-deferred compounding, because your ultimate goal is to have a successful career, provide for your family, and certainly provide for yourself, but build that retirement on day one. It's all about time in. Don't start late. And that was the secret to my success to being able to retire earlier than I actually did, was because my father taught me about tax deferred compounding, and time in the market is the key. So learn about that aspect for your own future.
Really good advice. Very good. We have another university student who says that he is not an engineer, but he is an amateur who has an interest in RF. So, what advice or suggestions do you have for him to stay active in the radio field as an amateur?
So this is someone who wants to stay active in the amateur radio field, but doesn't have a professional engineering background. Is that right?
Correct. So he's studying something else, but he wants to stay competent in RF as an amateur.
Okay. Yep. And you can certainly do that. That's readily achievable. What I would do is, one is I would achieve your extra class amateur radio license. Not that difficult to do, but there's good learning involved. Then I would start building your amateur station, not as expensive as it used to be. And the way to keep your skills current is to learn by actually doing. Build some antennas, make some measurements, experience radio wave propagation, and you will learn so much. And join a local radio club. There are, in any metro area, hopefully that's where you are, different clubs have different emphasis. Some are very public service oriented, which is fine. But there are always clubs that are very active in kit building, education, networking with professional engineers that are always building things. So get involved with a local radio club that has a technical emphasis, and you'll have projects to work on that will boost your learning dramatically, and you'll have experienced people to work with that can teach you things. But the key thing is to build your ham station. It doesn't have to be huge. You don't need a tower or any of that stuff, but start experimenting, building, and learning by doing. And there are great books available from the American Radio Relay League, the Amateur Radio Operator's Handbook and RF Design books that are beautifully written by the American Radio Relay League. Get those books and read them, and boy, you'll be an expert in no time.
Good advice. Yes, I have many of those ARRL books, and although I am an engineer, I found them very useful. I just recently acquired the second edition of the antenna physics book, and I wished I'd have had that when I was going through EE school, because it was much more readable than what I had as a textbook.
Right. That's a very key point, because while the textbooks have all the fine points and all the hard information there, the ones from the American Radio Relay League are written in a way that is so easy to understand. I use them as reference books, even to this day, to remind me of the basics and techniques in a quick study way that's so clearly explained.
Yeah, they do a very good job. So we have another question here about tube-based radio receivers and amplifiers. Do they sound better than semiconductors or not? As an engineer and an audiophile, do you want to answer that perennial question that comes up?
Sure.
Tubes or transistors?
Right. This is an excellent question, and I'll answer the RF part first and then the audiophile part second. So in general, for RF amplifiers, whether they generally, we're talking RF power amplifiers at some level, generally tube amplifiers are inherently more linear than solid state, simply because of the transfer characteristics of tubes. And so generally, they have lower intermodulation distortion than solid state amplifiers. So that is a true statement. However, solid state amplifiers don't require any manual tuning when you change bands, and they well-built solid state amplifiers have very long lives. You're not replacing tubes. and you don't have the high voltage power supplies involved. But tube amplifiers are inherently more linear than solid state. But that doesn't say don't use solid state. What that means is by quality solid state products, certainly solid state receivers are superior to tube receivers generally and very stable. But for power amps, tubes have less distortion. That is true. But solid state has so much more convenience, no tune, and just instant band switching. Now there is a new technology, new to amateur radio, that's starting to come into the market called distortion pre-correction, where you take a directional coupler on the output of your 100-watt amp in the radio that could be built in the sample, or a sample from your linear amplifier that could be tube, but certainly solid state. Bring that back to your software-defined exciter, and it will look at the waveform it's sent, and it'll look at the waveform coming out of the amplifier and say, oh, I see what the distortion is, and it'll distort in the opposite way to super linearize the amp. And this technology is just coming into the market. So that takes care of the distortion, the somewhat higher distortion in solid state power amplifiers in amateur radio. So they are solving that last problem. Now in the audiophile space, tube amplifiers, beyond the fact that they're tubes where you have to occasionally replace tubes and you have higher voltage power supplies, tube amplifiers have a certain characteristic sound. And it's not necessarily a more accurate reproduction than a high quality solid state audio amp, but it's a sound that oftentimes has even ordered harmonics at lower levels, and the even ordered harmonics add a sweetness to the sound. The human ear perceives that low level of even ordered harmonics as a pleasant sweetness. So while tube amplifiers can measure very, very well, they do take the maintenance of a tube, but they have a certain sound character that many people in the audiophile would absolutely love, because it just seems more true to life, sweeter, more natural sounding. The problem is you have to have a lot of tubes to make a lot of power to drive low efficiency speakers. Solid state amplifiers are very clean, quality ones. You can get enormous amounts of power. Personally, I've gone 100% solid state with my audio setup, but that's really a consumer choice in the audiophile field. There's no wrong answer there.
Okay. Good way to answer that one. I hear that regularly among us in electronics. So my dear friend Carl Schulte, who actually got me into Radio Club of America so many years ago, back in the 80s when we worked together at Motorola, he has an interesting question. He says his granddaughter is a junior at Virginia Tech. Her major is Russian and international politics. She's aiming to go into the State Department or become an intelligence analyst. To make herself more useful, can you recommend a survey of technology, like in communications and radar and so forth, that exists? Is such a survey course exist at Virginia Tech?
Boy, that's a good question. I do not know if there's a survey course, but what I would recommend, the Virginia Tech campus experience is excellent, and the faculty there are fantastic. I can't say enough good things about them, and I do spend time down there even now, working mainly with the college radio station still as an advisor. But what I would do is I would go over to the electrical engineering department and ask to talk to some of the high level folks and pose that question to them. Just, be assertive. Just go over and say, hey, this is what I want to know. Do you have a survey class? What can I do to better my prospects of building a career in this field? And I would like to talk to somebody, one of your senior people here, who can advise me on this. Don't be shy. And it may take a couple of tries, but you'll partner up with folks that will give you the best advice you could ever get.
It might even lead the university to consider a survey course for non-engineers.
Good point.
Because I know that there was a history of technology course that I took in my alma mater, as an elective, but that isn't what she wants. She wants current technology and where are things going, like with artificial intelligence, that question we had before with SDR and AI. So yeah, maybe Virginia Tech would consider offering such a survey course and even open it up to the world for that matter.
Or they
Uh,
may already have one.
yeah,
But
we
if
just
they
don't
don't,
know.
but if they don't, they should. That's a great idea.
Yeah. Okay, so we're coming close up. We got another 6 minutes, and we can take a few more questions. If let me see, I got a couple of others under the Q&A. So can you describe HAARP's primary objective and how it is progressing?
Sure, great question. Okay, well, I am still the part-time chief RF engineer for HAARP, and the site thankfully is working beautifully, and it's very reliable. We have excellent maintenance staff up there. And so, what is the primary objective? Well, HAARP is a radio science sandbox. It has capability from DC to light. Yes, we have domes, optics trailers, optics science pads. We have radar pads. We have satellite capability. We have HF, many antennas, many transmitters, many receivers, diagnostics, ionospheric sounders. It's just DC to light. So it's a radio science sandbox that happens to be in Alaska. So it doesn't necessarily have a singular purpose behind it, or even two or three. Now, it does have this large 180 tower array, a 12 by 15 phased array that we've spoken about earlier. That's an HF transmitting array, electronically steerable with any modulation you want, with 180 20 kilowatt each transmitters, one married to each tower, so a 3.6 megawatts input power, and our effective radiated power up at the high end of the band, which is 10 megahertz, because the vertical incidence maximum usable frequency rarely goes above 10 megahertz before the ionosphere vanishes. Oblique low angle radiation in HF, the maximum usable frequency or MUF can go up to 30 megahertz. But vertically firing as we are, it only goes up to 10. Okay, so one of the emphasis of that instrument is to have enough ERP, which tops out at 5 gigawatts, 97 dBW at the high end of the band. It's just enough to stimulate the plasma or the free electrons in the ionosphere to do cause and effect studies. And this is extraordinarily valuable for HF propagation experiments, for stimulating electromagnetic, useful, coherent RF at our modulation rate. For example, we could be transmitting at 4.5 megahertz, put a 1 kilohertz square wave as an amplitude modulation on all of our transmitters. So our 5 gigawatts is going up and down, let's say at a kilohertz. It could be 10 hertz or even 1 hertz. But we're modulating with a square wave at an audio rate, let's call it a kilohertz. And so our 5 gigawatt ERP is going up and down at a kilohertz, and we can stimulate RF out of the ionosphere at our modulation rate, in this example, 1 kilohertz. And it's weak, but it's useful. And we're trying to optimize that, learn the physics about it, and it opens up the door to ground penetrating radars, to ocean penetrating radars and communications, and other uses of low frequency radio waves that you cannot build a conventional transmitting antenna to do, because the antenna would be too long and it'd be too close to the ground for a useful pattern. So this excitation of the ionosphere for cause and effect studies is useful for secondary emissions of RF at our modulation rate, understanding the science and the physics behind it. We do ionosphere propagation studies, over the horizon backscatter radar work, and we can also create interference patterns in the ionosphere, so GPS and other satellite users can work on their algorithms to take it out.
That's great. So, Steve, we just got a few more questions and we're running out of time. So maybe you could answer these briefly going forward so we can finish them all. One of them is a very intriguing question that kind of was in the back of my mind as well. How was it that the architect of the Russian over the horizon radar system was actually able to leave Russia and go to the U.S.? How did he do that?
Okay, sure. I can answer that question for you. So there was a time period after the Cold War came to an end that immigration out of Russia was actually very easy. And there was a bit of a brain drain where people with, PhD level education, many folks, especially those of the Jewish faith, which Simon was, they felt like their lives would be better if they emigrated out of the life experience they had had in Russia. And so the door was open. There was no problem going. They were seeking a better life and more freedom and more safety in their lives. And so it was easy to leave, and it was very opportune. And so a lot of Russian scientists came to the United States, and they're brilliant folks. And I think they were just trying to achieve a better life, and there was nobody stopping them.
On the HAARP project, what were the power amplifiers? The finals, were they solid state? Were they tubes? What were they?
Sure. So of the HAARP transmitters, the output amplifiers are IMAC 4CX 10,000D power grid tubes, and there's two of them in a push-pull pair. They're grounded grid for unconditional stability, cathode driven. Of course, we have to have stepper motors to tune these. We have a stepper motor tuned antenna tuner as well. But we went with power grid tubes for two reasons. One, it was the lowest cost technology. We designed this in 1995, so it was the lowest cost technology that could meet our harmonic and spurious requirements without exotic switched low pass filters and all. But secondly, these tube amplifiers are extraordinarily rugged and durable. And there are times when we can't completely match, or the SWR changes, we can't match to the load impedance, and they can operate virtually into an infinite SWR with dynamic management of the tube parameters. So it was ruggedness, low cost, and meeting our harmonic and spurious specs, and that power grid tube technology was by far the way to go.
Wow, interesting. So one other thing, I guess this will be our last question because we're actually a little over time. This chap said he came into mathematics in an effort to understand Maxwell's equations. I'm still doing math, but I love amateur radio. Can you comment on the role of mathematics in learning radio science?
Well, mathematics is certainly a piece of any engineering application. And I would, that's a somewhat difficult question to answer. It depends upon what you want to do. But what I would suggest is that the radio sciences, in a general sense, half of it is practical, learned engineering knowledge to build things and make them work and make them reliable. It's a bit of an art, but it's a fun art. And then there's the mathematical, analytical side to analyze what you're receiving and hearing, and to predict what your designs can and cannot do. I would recommend getting involved with the ham-sci group, which is very, very active. And just look up ham-sci on the internet. It'll come right up. HAARP is partnered with ham-sci. I'm trying to make that more of an official partnership, still working to make that happen. But this is a group of amateur radio scientists, and they will help you learn the math that you need and the practical skills. An excellent organization.
Yeah, and they're going to be doing some work with the solar eclipse that's coming in April, I think it is. So there's a lot of interesting stuff they're doing. Steve, this was an excellent interview. We're getting a lot of comments that are very positive, best interview ever, and so forth. So this has been really, really great. I want to remind all of you that the next interview will be in March, and please let Amy know of any topics or suggested speakers, and we'll try to arrange for that. Thank you all for listening. And RCA is still around, so please join us whenever you can. Take care.